In today's lecture, we will talk about the second representation of Fourier series, and this representation is called amplitude and phase representation. So let's first look at its mathematical expression. Suppose that we have a particle signal xt with a period capital T. So xt can be represented as a0 plus infinite sum from k equal to 1 to k equal to infinite, with the summand ck multiplied with cosine k omega 0t plus phi k. So this representation is tightly related to the sine cosine representation that we have learned earlier. So let's recall for the sine cosine Fourier transform, Fourier series representation. So in this representation, xt is written as a0 plus the infinite sum from k equal to 1 to k equal to infinite with the summand ak cosine k omega 0t plus bk sine k omega 0t. The coefficients of these two representations are tightly related to each other. And actually, these two representations are equivalent to each other. Because of this equivalence, we can simply compare these two representations and obtain the following result. So we can get ak cosine k omega 0t plus bk sine k omega 0t. This expression should be equal to ck cosine k omega 0t plus phi k. So next, by using the property of cosine function, we can write it as ck cosine phi k cosine k omega 0t minus ck sine phi k sine k omega 0t. So by comparing the first line of the equation and the last line of the equation, we can simply obtain the following result. We can find that ak should be equal to ck cosine phi k, and bk should be equal to minus cosine sine phi k. So therefore, if we are given the amplitude and phase representation, we can easily calculate the coefficient of sine cosine representation. Now, on the reverse direction, if we have the value of ak and bk, and we are trying to calculate the coefficients ck and phi k for the amplitude and phase representation, we can use the following formulas. So ck is equal to the square root of two quadratic terms of ak square plus bk square. And phi k can be expressed in two formulas. So if ak is larger than 0, then phi k is equal to minus arctangent bk divided by ak. So now if ak is smaller than 0, then phi k is equal to pi minus arctangent bk divided by ak. So here, this term represents the inverse function of the tangent function. So it is also written as arctangent function. So now let's continue to introduce another important concept after we have the amplitude and phase representation. And this concept is called spectrum. So spectrum is also called spectral plot or frequency domain plot. So one example is the amplitude spectrum. So let's look at this. So for the amplitude, it's represented as CK, and it is called amplitude spectrum. So we know that in the Fourier series, we will only have the frequency terms that are at the DC frequency, which means it is a frequency 0. And then we have a frequency f0, and the frequency twice of f0, 3 times of f0, and so on. And the value of CK can be obtained by computing the coefficient of the Fourier series. So we can represent CK as the following lines with an arrow. So this is a typical way to express amplitude spectrum. And similarly, we can also have another spectrum for the phase. So the phase spectrum can be represented similarly. So I guess the line is not really straight. Let's plot it again. Okay, so now it's orthogonal to the frequency line. So this is a phi k. This represents the phase spectrum. And the phase may have different value, positive or negative value at different frequency. So this is f0, this is twice of f0, this is 3 times of f0. So you can use the circled lines to represent the spectrum, or you can use the arrowed lines to represent the spectrum. So such spectrum, you can find it on the textbook. So here let's simply write it in the form in the textbook. So you can simply write it in this way, which is the straight line. Now, why this amplitude spectrum and phase spectrum are useful for us? So first of all, CK as the amplitude spectrum, it actually combines the value of AK and BK. So it combines So recall that ck is equal to a squared plus b squared, and then take the square root. So if ak is equal to 0 and bk is not equal to 0, so ck will not be equal to 0. So therefore, even if one of the terms ak and bk is equal to 0, ck still represents the fact that you actually have a term at the frequency k times of f0. So therefore, ck represents a very good way to help us to find the useful frequency components that is contained in the periodic signal. So in practice, we usually use ck to quickly find out the key frequencies. And phi k as the phase spectrum it actually provides additional phase information. And this additional phase information is not really contained in ck. Now, if we look at this, these two figures again, we can find that it represents a plot for different frequency. So this is tightly related to the previous view that we have, that when we plot a signal, we can plot the signal in time domain with a varying time variable. And now we are plotting the signal in the frequency domain with a varying frequency. So this provides us two different ways to vision the signal. So this is another important point. So time domain and frequency domain plots provide two ways to view a signal. Now let's consider one example. So let's again consider the pulse train model, the pulse train signal. So let's plot it. This is a signal that has a pulse, rectangle pulse like this, and its period is capital T. The duration of the pulse is tau. And for the next period, we will have another pulse. This signal looks like this. So this is a signal xt, and the amplitude of the signal is A. And now let's provide the value of this coefficient. A is equal to 2, tau is equal to 2 and the capital T is equal to 8, and the unit is second. So from our earlier lectures, we can find the coefficient of of the Fourier series representation for pulse train. So at that time, we obtained A0 is equal to A times multiplied with tau divided by capital T. And AK is equal to 2A divided by K omega 0 capital T multiplied with the sine K omega 0 tau. And BK is equal to 2A K omega 0 T 1 minus cosine K omega 0 tau. So this is the coefficient of sine cosine representation that we obtained in our earlier lecture. Now, if we want to find the coefficient for the amplitude and phase representation, we need to calculate the following formula. So CK is equal to AK squared plus BK squared, and then take the square root. So this will be equal to 2A divided by K omega 0 tau multiplied with sine square K omega 0 tau plus 1 minus 2 cosine K omega 0 tau plus cosine K omega 0 tau square, and finally take the square root. So now we see that within this summation term, we have a sine and we have a cosine term. We know that their summation will be equal to 1. So this allows us to further obtain the following formula. This is 2A divided by K omega 0 T multiply with the square root of 2 minus 2 cosine K omega 0 tau. Now, by further using the properties of a cosine function, we can further get this is equal to 2A K omega 0 T multiplied with the square root of 4 times of sine square K omega 0 tau divided by 2. And therefore, we get the formula that is equal to 4A K omega 0 tau. No, it's not tau. I'm sorry. It should be capital T multiplied with the sine K omega 0 tau divided by 2. And then take the absolute value. So this gives us the expression of CK. Now for dk, we can calculate the dk as 2 cases. So in the first case, it's equal to minus arctangent bk divided by ak. Now for the second case, or the condition for the first case is that ak should be no smaller than 0. And for the second case, it is equal to pi minus arctangent bk divided by ak. So this holds for the case of ak that is smaller than 0. Now, if we substitute the values of the signal coefficient, a equal to 2, tau equal to 2, and capital T equal to 8, we can obtain a simulation figure for the amplitude and phase representation of the phase pulse train. So suppose that we consider such kind of simulation figure. So let's find one here. Okay, so this simulation figure is provided here. So this is the case of a partial sum of the Fourier series with n equal to 10. So in the first figure, we plot the partial sum in the time domain. And in the other two figures, we plot the spectrum. The second figure would be the amplitude spectrum. And the third figure is the phase spectrum. So the amplitude spectrum is represented by CK. So recall that we mentioned that CK is a combination of AK and BK. So once we find that CK has a relatively large value, we know that we have to find one key frequency of the signal. So for example, we can find that C1 is a relatively large value. So this means F0 is an important frequency. So therefore, the amplitude spectrum can help us to quickly find the key frequencies. So I also want to emphasize that it does not mean the amplitude spectrum is spectrum is important and the phase spectrum is not important. Actually, the phase spectrum is also important. It provides additional information that is not included in the amplitude spectrum. And for that, I think you will learn that part in later courses. So with this, we finish